time, regardless of the number of participants. We encourage all participants interested in a particular mini course to attend all lectures and all activities associated with that mini course to get the most out of it. With that being said, we are very excited to have Federico Vigolo speaking on expander graphs. Whenever you're ready, Federico.
Hey, I am ready. So first off, thank you very much for the invitation. It's very nice to speak at this Zoom conference, and it's nice to see so many participants already, so that's great. Yeah, it's going to be interesting. This mini course is about expander graphs, and I wrote here some references. In particular, a very nice reference is the survey by Huri, Lina, and Victorson. So if you want to know more about expanders, I recommend it. It's a very pleasant read. And then there are a few further reads that are suggested here. And at each lecture, I will give you some more references that are more relevant to that specific lecture. So let me begin with the plan of the mini course very briefly. So today we are going to, well, do a little bit of introduction and give a definition of expander graphs. And then we are going to do one application of expander graphs to computer science, well, more or less, which is error correcting codes. And this topic is quite independent from the rest of the course. So this will not come back afterward. It's just serve as a motivation because it's a rather neat theory. And then the next time, that is tomorrow, we are going to discuss about the spectral characterization of expanders. And then we will give some explicit constructions. So this lesson will be a little bit more analytic. And then finally, we will go more towards coarse geometry, talking about coarse embedding into Hilbert spaces and Gromov monsters. Okay, so let's begin with a slogan definition, which is also the definition that I gave in the abstract. That is that expander graphs are sequences of sparse yet highly connected finite graphs. So what we gain from this, we gain that we care about finite graphs, but since this is finite graphs are coarsely trivial, so we want to add some more interested to it. We want to look at arbitrarily large finite graphs. And so to go for arbitrarily large, then we need to pick sequences. So we are looking at sequences of finite graphs. And then we will care about properties that hold uniformly as you move throughout the sequence. So we care about uniform properties of families of graphs. And then there are other two keywords, that is sparse and highly connected. And sparse is actually very easy to explain. We just want the graphs to have bounded degree. And again, since you care about the uniform properties of the sequences, then we want uniformly bounded degree. And highly connected is the more interesting word. And there are at least two meanings that one can give to it. And so one meaning is what one would expect, that is, these graphs are hard to disconnect. Which is the point of view we're going to take today. But then there is a different point of view that is also very useful. That is, roughly speaking, that it is easy to walk around the graph. And those two points of views are indeed equivalent. And so, as I said, this is today, and this is tomorrow. Okay, so now that we've done a little bit of introduction, we can actually start with some definitions and notations and stuff. Okay, so notation. G, calligraphic G, will always be a finite graph, and it will usually be connected. And we are fine with loops and multiple edges. We don't really care very much. So this is here you can see a typical graph. What do I want to say? Yes, for convention, we identify G with its set of vertices. I mean, by this, I just mean that if I say the cardinality of G, I means number of vertices. And if I write that A is a subset of G, this means that A is a subset of vertices. Okay, so convenient notation. And then we write by the degree of the graph G is the maximum of the degree of its vertices, or the valences if you prefer. So V in G means a vertex. Okay, and now given a subset of vertices, we define its boundary. And so we are about 7 minutes in, and the geometric group theory without boundaries already failed. So here we have first boundary. So the boundary of A is just equal to the set of vertices in the complement A that are linked to the inside of A. So for which there exists a vertex in A and an edge connecting W and V. So by this symbol, it means that there exists an edge. So picture, say that this is our set A. Then its boundary, oh, too big. That one has better. Okay, so that this is our set A. Then its boundary is going to be all the vertices outside that are connected to something in the inside by some edge. So there's this edge here, and then, oops, edge is going out. So that this is the boundary of A. So far, so good? All right, so this was some notation. And now let's get, well, maybe I can start like this. I can start giving a real definition. And it is the definition of the Cheeger constant of a graph. The Cheeger constant of G is defined as, well, it's a number, and it is the minimum.
Federico, there's a question in the chat.
Wait,
the question is the boundary
okay,
the graph with the edges?
Yeah, it's a valid question. For us, the boundary would be the vertices. So if you want, that's it. Yeah, the boundary is just the vertices. Depending on what you're looking at, there are instances where it is more convenient to have the boundary to be the edges. But for this mini course, I decided to go for vertices. Thank you for the question. Should not have thrown the vertices. I should not have thrown the edges. So let's go. This is the vertex boundary. Okay, so the Cheeger constant of the graph. So if you want, it should actually be the vertex Cheeger constant, because often the Cheeger constant is defined using the edge boundary, but we care about the vertex one, is the minimum of the ratios of the cardinalities. Right. Let me write it and then comment on this. So A is a subset of vertices with cardinality of A at most half G. Okay, so what is this? We are picking all the subsets of vertices that have cardinality at most a half the total cardinality of vertices. And we're looking at the ratio of the size between the boundary and the set. And we're minimizing this over all the subsets. Basically, we have that h of g is greater than some constant epsilon, if and only if, for every subset, let me say, the size of the boundary of A is at least, well, it's greater than epsilon, the size of A. So it is an isoperimetric kind of inequality. It's okay. 3 equality, which says that once you know the size of the set, you have a lower bound on the size of its boundary. And in particular, if you have, like, the trigger constant will be a measure of how much you see things of this sort. Like if you have two big components that are separated by only few edges, this means that you're going to have a small trigger constant. I'm going to give more example right now. Yeah, maybe I can start giving some examples. Yes. So first off, as a sanity check, we have that. So we claim that the trigger constant is a measure of connectedness of the graph. So first off, note that the trigger constant is equal to 0 if and only if G is disconnected. Because it's enough to let A be a connected component. And then its boundary is the empty set. Well, I guess this is one implication. It's the implication, this implication here. And the other implication is just as easy. So, okay, we have this sanity check. Okay, let me add a remark that some of you probably already seen a similar condition, and it is when the graph is infinite. If the graph is infinite, then the trigger constant, I mean, you can define an analogous trigger constant, and this one is positive if and only if the graph is non-amenable. And if you want, this is the Follner condition for amenability. It's just a restatement of that. So this is for those who already know what non-amenability is, and for the rest, just ignore this remark. And let's see, oops. Write some more explicit examples. So, for example, let's just compute some trigger constants to see what happens. First off, let's start with a 3. So this is the 3 that has a binary 3, rooted binary 3 that has n levels. So this thing here. And we want to estimate the trigger constant. And there is one natural candidate to check. That is, if we pick one big set, that is, we want to cut away this edge, then the boundary of this big set is just one vertex, so that we have that the trigger constant of this graph is at most 1 over the size of this set, which is 2 to the n minus 1. And actually, this is easy to check that this is actually equal. So this trigger constant is very small when n increases. Okay, this one first example. Then the second example is just a circle. So again, if we want to find a big set with a small boundary, like small in proportion to the size of the set, then the natural thing to do is to try to cut the circle in half. So again, let this be your set A. Okay. Then this set is telling us that the trigger constant of this graph is at most, say, 2 over n. Yes, because there are 2 elements in the boundary. Yes, so it should be a 4. Okay. So the trigger constant is twice, because there are the 2 elements in the boundary, divided by the size of the set A, which is n². So we actually get 4 over n. So again, it's something quite small. Now let's start taking products. And so this graph here is the product of two cyclic graphs. So you should see it as a torus. We are identifying the edges. Well, we actually realized that despite being like despite looking like a more connected graph, it is actually not really, because we can pretty much use the same subdivision of before. That is, before we break a cycle into two halves, and we can do the same here. This one. We break each cycle into two halves. I mean, we choose one direction and we break that cycle. And so we see that we get the same estimate for the Chiger constant. So G is more or equal than 4/n.
There is a question, Federico. When you choose A, the subgraph on A needs to be connected? Oh, okay, it's been answered.
It was answered? Okay.
Yeah.
No, A does not need to be connected. No. You take the minimum over all the A, but it will generally be convenient to pick a connected A, because yeah, if it's disconnected, it probably has a bigger boundary than it would have if it was connected, but it's not necessary. Anyway, what I was saying here is that here we just noted that taking the product didn't do much. So, and this is actually a general fact, that is, if you define the Cartesian product of two graphs, like this way, by adding edges, if you move in one direction or the other, then the Chiger constant of a product is smaller, well, it's probably equal to the minimum of the Chiger constants. Minimum of Chiger constant of G1 and Chiger constant of G2. So this is in general. Okay, and the last example is where you have a complete graph. So Kn is the complete graph, and here you see that for anything you pick, you're going to have everything else as a boundary. And so since you're just restricting to subsets that are at most a half the total size of the graph, then we get that the Chiger constant of Kn is nothing but, I mean, is already equal to 1, because you start with a set that is at least a half and everything else is in the boundary. So the boundary is at least as large as the set you were starting with. And the remark I wanted to make is that in all these cases, well, I actually wrote families of graphs depending on n, and we had that the Chiger constant would go to 0, or the degree of these graphs go to infinity. So we have the 3 cases where it goes to 0, this one, and this one, and then one case where it goes to infinity. So let's say 0 and degree to infinity. And so, yeah, so now we give a definition, and we say that a sequence of graphs is a family of expanders so a sequence of graphs Gn is a family of expanders if the conditions, we want them to be larger and larger because we like infinite things. Then we want the degrees to be uniformly bounded. So this takes rid of complete graphs. And then we want that all the graphs share a lower bound on their Chiger constant. Okay, so none of the families that I drew before is going to be an expander graph because of the remark I just said. Either they have very small Chiger constants or they have very large degrees. And so the natural question is, do there exist expanded graphs? And when I say expander graphs, I implicitly mean a family of expander graphs. And of course, the answer to this question is yes, otherwise we will not be having a mini course, but it is yes in a rather spectacular fashion. That is, if you pick let Gn be a sequence of connected, say, D regular graphs for some D greater or equal than 3, but moreover, not any sequence, but a random sequence of connected irregular graphs, then it is almost surely a sequence of expanders. That is, this one is one of those, okay, this is one of those annoying situations where the generic object is what you're looking for, but if you're trying to construct one explicitly, that is very hard. In fact, we are only going to see an explicit construction tomorrow. And the problem in finding explicit constructions is that the trigger constant is very, very hard to compute. That is, you have to take an infimum over all the subsets, which is clearly something. Yeah, I see the question. The irregular graph means that every vertex has valency D. Degree of B equal D for every vertex. Okay. So expanders do exist. And tomorrow we're going to see the construction, while right now we are going to see an application. So now we're going to change topic for a bit and try to discuss something a bit more concrete. That is, more than an application of expanders, this is an application of the idea of expansion, as we will see later. So the application that I want to talk about is about error correcting codes, and more specifically, low density parity checks. That is, we start off with a concrete problem. And the problem is that we need to send a message through a noisy channel. So, where the model we are using is the following. That is,
so there is a question in the chat.
Yeah.
It asks, how do you?
Yeah. Good question. I actually not completely sure what the theorem of Pinsker actually say, because I think it's written in Russian. But in the exercises, there will be one model of, well, so in this specific case, we are, okay, so let me be a little bit more precise. In this specific case, you first choose the sequence. So choose a sequence of cardinality. Okay, so sequence of, how do I write, n of n, and then pick Gn at random, uniformly at random. This is now as a finite graph, uniformly at random among connected irregulars. Irregular graphs of cardinality equal to n over n. That is, this now is the set of connected irregular graphs with n components, n vertices is a finite set, so you can pick one at random. Okay, and I was saying that I will be suggesting as an exercise to special case of this theorem, I mean, to prove that in some sense, some random bipartite graphs are expanders. I'm not completely sure what is the original statement, but some statement you will do as an exercise. Thank you for the question. Okay, back to our application. So we want to send a message through a noisy channel. And so how do we model this problem? That is, the message is a sequence of bits. And the noisy channel means that when you do the transmission, some of the bits may be flipped. There might be some random bit flips. So, for example, here we have one input message. So this is our message. And then we do a transmission. And during the transmission, some noise happened, and we see that there are some errors. And this is not good because we want to send out the message correctly. So we want to find, so how can we safely send the message? Well, the solution is that we need to add some redundancy. Okay, so one obvious way of adding redundancy is just to say repeat. So you start with your message, and instead of sending the message, you start by repeating. You send a different message where you repeat each letter many times. For example, here you pick your message and you repeat each letter 3 times to get a longer message, and then you transmit this longer message. And again, some errors occurred. But then when you want to decode the message on the other side to recover the original message, you just use the majority rule in this case. So here you have 0, 0, 1, so it is more likely to be a 0 than a 1. So this is probably a 0. And so these ones are all 1, so it must be 1. So 0 and 0, 1, and more 1s than 0, so it probably is a 1. And again, 0, 1. And I actually recovered the correct message in this case. So this protocol did work in this case. But there are 2 obvious problems to this specific solution. And one is that it is very inefficient. That is, I am sending a very long message. But worse even is that it is still not robust. In the sense that it's enough to have 2 errors, 2 consecutive errors. Errors break it, because then the bit flips. And so the solution would be to concatenate even more letters and repeat even more, but then this makes it even more inefficient. So this is not a great solution. And what we want to do is to find a better way to encode a message and send it through in such a way that when we receive the outcome of the encoded message, we can decode it and be reasonably confident to obtain the message that was sent off to begin with. So let me schematize this problem a bit. So here it is. What we do, we have the following. We start off with a set of messages. So set of messages of length m. That is, we want to send n bits of information. And what we do, we first started by encoding it in such a way that we obtain a subset of the set of messages of length n for some n greater than 2, n greater than m. And basically, we are selecting a subset C of the set of all messages of length n, so that each one of these, each element in this set C corresponds uniquely to one message of length m. This is the encoding procedure. And actually, this subset is called the code. So a code is just a choice of a subset of messages. Among all the messages of length n, I choose a subset of cardinality 2 to the n. So cardinality 2 to the m, and each one of these is uniquely corresponding to a message of length. Yeah, that way. Okay, so now that we have the code and we have a way to associate to a string of m symbols a much longer string with n symbols, then we transmit these new symbols, and here some noise might happen. But no matter what, we end up again in the set of messages of length n. And at this point, we want to do some decoding. That brings us back again to the set of messages of length m. And we hope this procedure to be robust. That is the specific problem we want to solve. We want to find a good code C, a good code C, such that it is as large as possible. Meaning that we want n should not be too much larger than m. For example, a good thing could be to have that m and n are linearly dependent. So we want to have a large set C so that when we send the transmission, we can send relatively few extra bits. And then we want it to be robust. So we want that it takes many errors to corrupt the message. Okay. Yeah. And for notational convenience for later, is that since our messages are sets of bits and each bit is either on or off, we can identify it with elements of f2 to the m, where it is the fields into elements. So it is just 0, 1. And we take the m power. So each message is an element of f2 to the m. And again, this message of length n is an element in f2 to the n. And so the code C will be some subset of f2 to the n of cardinality n 2 to the n. Okay. Next, a little bit of notation is that we can define a distance on the set of messages. Distance between two words. W prime in f2 to the n to be equal to the number of differences so that we have the word that is 1011001 and then 11011000. Then this differ here and here and here and here and here. So there are 5 differences. So the distance is equal to 5. So this W and W prime. Oops. And this distance actually goes under the name of Hamming distance. Okay, and why did I introduce a metric in the set of messages? Is because we have a natural decoding algorithm, which would be just once you receive a message, that is, you are in here, and you want to get an element of a message of length m, and you know that you were being sent an element of c, and then you get some random noise, and you have to make a guess at which element of c you were sent, and the natural choice is just pick the closest one. The coding algorithm is just pick the closest element in C. And this will determine you a message of length n.
Sorry, Federico, there's a question. Can you clarify / repeat what is meant by as large as possible?
Okay, this is not mathematically precise. This is Okay, so this is not mathematically precise, but basically the thing is that when you want to send a message, you want to send a message of length n, and then you're actually sending it along a cable. And to send a long message, it takes a long time, and you want to save the time. So, like, if you want to be sure to be sending the message correctly, you just send the same message many times, and until you're fairly sure that at least one of those times was correct. But this is going to take you a lot of time. What you want to do is that you want to send a message that is not that much longer than what you were starting with. So in this sense is what I'm saying, is as large as possible. Well, even more precisely, what we're doing here is we're changing the paradigm. Instead of looking at the sequence of length n and see what is the number n that you need. So instead of fixing m and then looking what is the n large enough that works, we do the opposite. We fix first n. So we say our communication is going to be of length n. And then we ask, how many messages can we send, can we safely send within that length of a message? That is, we're trying to choose a set of possible messages inside of your predefined length, and you want to be able to send as many messages as possible. So in this sense, you want C to be as large as possible inside your predefined length. Does this answer the question?
So is it fair to say you want C to be large relative to the box to the right of it?
Yes, precisely. Okay. Yes, thank you for the question. I was not very clear. Okay, so am I doing on time? Okay. Okay, now that you've seen this decoding algorithm, note that if you know that the distance between any two elements in the code is at least r, then this means that if we do up, well, then the code, okay, then the code can withstand at least r/2 errors. Because if you do r/2, each error is going to flip one bit. And so it will increase the distance between the original word by 1. And so if you only make r/2 errors, then you're still going to be, well, actually r/2 minus 1. If you make less than r/2 errors, it means that the closest point to inside C is precisely the point you were starting with. That is, if you make at most r/2 minus 1 errors, then the decoding algorithm is going to recover the correct message. That is, assuming that the distance between any 2 points is at least r. Okay, let me draw a little bit of a picture. Oops. Yeah. So that we have the set of messages that are being sent, and then inside here there is the code, set C. C is just some subset inside, and we are assuming that all these distances are fairly large. Then when we send the message, we make some errors, but each error is at most at distance 1. And so if we didn't make many errors, we're still inside the ball here. Now, okay, this picture is out of scale, so let me just do 1 error. And we see that the original point is still the closest one. And so when we decode, we are going to get the correct one. And so if we take this point of view, then the notion of to choose a code that is as large as possible, what we want to do, we want to find the set that is very well distributed inside F. So we need C to be well, large and with big distance between elements. So we want it to be sparse in F to the N. All good so far? Yes, good comment. Yes. Okay, so now we see, let's have another look at our naive code where we were just repeating each letter k times. Then in this case, we can say that the error tolerance is equal to k/2, where the error tolerance means the number of error that it takes to break the code, to corrupt the message. And if we just repeat each letter k times, if we do k errors and we are unlucky, then we corrupt the messages. So the error tolerance is strictly dependent on k. And the relative size of m and n is just that m was equal to n over k, where again m is the n is the length of message that is sent, and m is the length that you wanted to send, or more precisely, you're sending you can send 2 to the m messages with 2 to the with n bits. I should have chosen different letters. M and n are very difficult to make them. It's very difficult to make them sound different. Anyway, the point of this naive code is either this ratio is bounded, and so it means that we're not being very safe because it takes very few errors to corrupt the message, or the ratio between m and n goes to 0. That is, if you fix k, then if you fix k, then you can only fix as much as k half errors. And if you want to fix infinitely, if you want to be able to fix a bigger number of errors, then you have to reduce the size of your code. And so you're being able to send fewer messages. And so in this sense, that naive code is not very good. More precisely, the question that we ask is, can we find a code C inside f2 to the n, such that, well, we want this ratio here is just the logarithm between this of the logarithm base 2 of the size C over n. Okay, so if you pick the logarithm base 2 of C, this is what we used to call m. But now we are forgetting about our initial set of messages. We just look at the code C. And so we're asking whether we can find a code C that is large inside f2 to the n, and large means that this, yeah, means this thing here, that if we pick the logarithm, if we compare the logarithms, they are on a linear ratio. Okay, such that, okay, so we're asking, is there a code that is large in this linear sense, and so that it can correct say at least epsilon to n errors. That is, we're asking for it to be able to correct a number of errors that is linear with the size of the message, and which should be compared with this one. Here, the naive algorithm is just giving you a constant number of errors, while we're looking for something that becomes the safer and safer the longer n is, and without spoiling the ratio of the information you can send. And so since we're using the decoding algorithm where we just pick the closest element, then this being able to correct, so being able to correct epsilon to n errors means that the distance, the minimum of the distance C prime, where C is different from C prime and they are in C, is at least epsilon to n. Well, it should be twice, but let me ignore the 2. And also let me call this minimum just d of C, that is the distance of the code. That is, repeating again, we're asking whether we can find a code that is linearly large and that has linear distance. And the code will depend on n. And the answer, unknowingly, is again, yes, by counting arguments. You can do some easy estimates, and this tells you that, yes, there exists some. But now we have more problems because this is a concrete problem, so we need explicit code C. And furthermore, since this is a problem in computer science, we would like the encoding and decoding algorithms should be fast. And there is one, there are many solutions, but one solution that we care about today is given by the low density parity checks. And here is where expansion will come into play. So how am I doing on time? Kind of short, but it's okay. Okay, all good so far? Is the problem clear? We're trying to find a big subset of f2 to the n where all the elements are at big distance from one another, where big means linearly. We want to find the linear bound that depends linearly on n. Okay, So we start off with a simplification. Since we're looking for a subset of, well, a vector space, we can look for a C, a code C, that is a vector subspace. And such a code would be called a linear code by a linear algebra. Well, if you have, in particular, if you have such a linear set, we can describe it by choosing a basis, or alternatively, we can describe it in terms of a matrix. That is, there exists a M times N matrix, which I call M, such that C is equal to the image of M, or if you want, is equal to M times F to the N. This, you can describe your code as, well, you have your big matrix M, that is M times N, and then you have your small vector M that you want to encode. This is the message you want to encode. And to encode it, you just do the matrix multiplication to get a vector of length N. And in particular, this is telling us that we do have a nice encoding algorithm. So if we pick a linear code, we have that. Good. So in particular, let me say this is one of the benefits. So one of the benefits of looking at linear codes is that there is an easy encoding algorithm. Okay. What did we write there? Okay. Then also it is. Oh, I was reading at the wrong slides. Okay. Yes. Then it is easy to see what is the size of C. The size of C is just equal to the, well, if we pick an M times N matrix, then the size of C is, we assume that the matrix has rank N. So the size of C is equal to the rank of the matrix, which in this case is just equal to 2 to the M. And that is the rate that we were looking for, that was log 2C over N is just equal to M over N. Okay, so it is easy to check the size of such a code. And by the way, this rate is called, this ratio is called the rate of the code. If you want to do some reading on codes, which is actually quite interesting stuff. But the very big benefits for us is that, okay, we are looking for codes that have a large distance, and this distance is defined as the minimum over all the distances among all the pairs of elements, and which is hard to check. But if you restrict to a linear code, then this is much easier to check, because the distance of the code, since you are in a vector subspace, you can just subtract and assume that one of your words is just a 0. That is, if you want to check the distance of all the pairs, the set of all the distances of all the pairs is just equal to the set of distances of elements from the 0 word. That is what I'm saying is that the distance of C, minimum of the distances of all pair, is just equal to the minimum of the distances between the 0 word and C, where C belongs to the code. We removed one variable, and this makes it much easier to check, unsurprisingly. Okay, and we claim that what we're going to find, the code we're going to construct is a code of this sort. And so we are going to use these benefits to find our actual code. And here is an alternative point of view on such a code. Here I described it as the image of a matrix, but instead of looking as the image of a matrix, you can also see it as the kernel of a matrix, of a different matrix. So that is C is equal to the kernel of some different matrix K. So where K is K times N matrix of rank, I guess N minus N. That is, instead of describing the image of M, we're just looking, since we want to say what is C as a subset of F2 to the N, we just describe it as the kernel of some matrix of this form. Small k. Okay. And if we take this point of view, then we see that the distance of the code C, which again, well, let me write it again, is equal to the minimum of the distance of W in 0, where W belongs to the kernel of K. Well, and it's not in 0. Yeah. Okay, and that is, if you want, it is equal to the minimum of the number of the minimum of the number of columns that add up to 0. Well, let me just ignore this. Okay, I just rewrote it for no reason. But let's just take this point of view. Oh, I'm out of time, right? And so now graphs come in. And the point is that we can, so let me take 5 minutes. Okay, so we had started the discussion. So this mini course is about graphs. And now we discussed a concrete problem, which was requiring for some subset of F2 to the N. And we are choosing a linear subset. I'm describing this linear subset as the kernel of some matrix. And now the link between graphs and matrix is given now. That is, we're looking for a K times N matrix. And we can find such a matrix if we're given a bipartite graph. That is, we have a graph that has two sets of vertices, so that there are no edges within those two vertices. And one of these sets, let me call it this set VL, this has K vertices. So cardinality of VL is equal to K, and the cardinality of V to the right is equal to N. And to such a bipartite graph, we get a matrix K of G that you define. I mean, we want it to be a K times N matrix, where at the element ij, I put 1 if, well, the left I, so the ith left vertex is linked to the jth right vertex. So this is edge, and 0 otherwise. Okay, so this will produce us a K times N matrix that has some 1s and some 0s. And the remarks is that now the elements in F2 to the N minus 0 are in one-to-one correspondence with non-empty subsets of vertices in the right. Because just by giving 1 to a vertex if you have it, and 0 if you don't. So there is this one-to-one correspondence. And then K of W, so matrix multiplication is equal to 0 if and only if for every I from 1 to K, the number of vertices in the right, that is the number of R to the J, that belong to A, where A is the set that is in correspondence with W. So, and for which Li is linked with an edge to Rj is even. That is, this number, that is the numbers of elements in R to the J that belongs to A and are connected with an edge of Li, is precisely equal to the ith coordinate of the product multiplication. This is just the product matrix. And so this is 0 in F2 if and only if this is an even number. So that is, we can, and this is the name parity check of the code. These codes are called low density parity checks because doing the matrix multiplication in this setting is just checking the parity of some set of vertices on the right. And okay, and the distance of C is therefore equal to the minimum of the size of A, because the size of A is just equal to the distance between 0 and W, where again W is the word that is associated with A. And we're taking the minimum over all the non-empty subsets. And such that Li has an even number of neighbors in A.
Federico, you have a question. How are the W and the A related in the first remark?
Yeah, okay, I was saying that, so an element in W is a sequence of ones and zeros. And an element of A, A is a set of vertices. And you use the indicator function, that is you have your vertices, so you have your n vertices, and then you have some set A, and then you say that the elements that are, the vertices that are inside A will be given 1, and the elements that are outside will be given 0. And so you have, it's the Boolean correspondence between subsets and strings of zeros and ones. Okay, so let me just say the neat remark. So assume that, did I call it A? Yes. Assume that for every subset A for every set of vertices on the right, you know that the number, well, you look at its boundary, which is going to be a subset of vertices on the left, and assume that this is always strictly larger than, strictly larger than d half A. Well, so let me first say, assume that the graph G is deregular for convenience, and that for every subset on the right, the size of its boundary is at least, it's strictly bigger than d over 2, the size of A, and it is, this is our notion of expansion, which is why I say that there are expanders. Okay, we're asking that this happens for every subset on the right with size at most d, some big constant d, then the distance of the code is at least d. And why I say that this is a neat remark, I say that this is because the proof is just that proof. So for any set in V to the R with size at most d, and which, by the way, corresponds to all the words in F2 to the N that are at distance at most d from the 0. Okay, for any such set, there exists an element on the left, so there exists L of I. So there exists I such that L of I has exactly one neighbor in the set A. And this is just by a counting argument, because if you don't have, I mean, if you have more than one neighbor, then you must have at least two. But since the degree is bounded by d, and here you have this d over 2, then you must remain with something else. So there is at least one element that has only one neighbor in A, because otherwise you couldn't possibly make up all the size of the boundary. And so since it has exactly one neighbor, then in particular it is an odd number. And so the word associated with A is not going to belong to the code. And so this is showing that the code has distance d. And now I'm out of time, so let me just say that, okay, I was hoping to state the theorems, but I will not write them. I will just say in words that there exist graphs that satisfy this property. And so in particular, these graphs do give you codes that have this linear bound both on the distance and on the size. And I'm over time, so I will stop it here. I had a few more remarks, but that's it. And then tomorrow we will start with a different topic. So this was an excursus where I just wanted to show, I mean, the real point of this second half of the talk was this neat remark. So that having very big expansion on one side gives you this exactly one neighbor condition, which I did not explain properly, but it is very easy. And so if you're not convinced, then it is an exercise to check that you do have this implication. And these neat remarks allow you to then construct a linear code, which I find it's a very, very cute trick.